very lucky to have Patrick Massot here. He's long been a leader of the lean formalization community. He has led things like the sphere reversion project and many other things. But not just that, in addition to formalizing stuff, he has created this lean blueprint format where he wrote a Python script, so which Steady Tau raves about and so on. So everyone uses that. He found interesting ways to teach using lean, using a controlled natural language. So has been one of the leaders in making lean more useful, making it easier to formalize, and also have a sense of adventure. So we'll hear Patrick will talk today about why Formalise Mathematics, and just a reminder, he'll talk tomorrow in the department on lean for teaching at 4 o'clock.
Yes, thank you very much, Siddhartha. Thank you for the warm welcome and also for the invitation, and also thanks to the other organizer. It's really nice to be here. It's my first time in Bengaluru. I'm amazed by this beautiful campus that you have here. I'm very happy to be here. And I'm here, and it's not obvious that I would be here because I was not at all doing formalized mathematics 10 years ago or any kind of computer-related things, really. I'm trained in the symplectic topology, so a branch of abstract geometry. And in this branch, we have many people who like geometric reasoning without, I mean, let's say, without all details. And my ordinary mathematical heroes are people like Yasha Eliashberg or Misha Gromov, and they are not really into formalized mathematics. So what happened to me? So why formalizing mathematics, and what happened to other colleagues as well? And I think it's good to discuss this. Why are we doing all that? And that's the main topic of my talk. And so I can already say something very important. So even if you fall asleep after the first slide, you get some message, some important message. Our goal is to extend the toolbox of mathematicians, and we don't want to remove anything. So I still think that Eliashberg and Gromov are my heroes, and they are great, and I'm not saying that what they do is not mathematics because it's not formalized, it's not rigorous enough. That's not at all the point. So we want to add more tools, and without removing anything from what we like, from the intuition, from the human part of mathematics, the interactions between humans, and all the discussions, the pictures. We keep all that, and we want to add more tools coming from formal methods. So today, I will show you what it looks like, because nobody so far showed any actual lean code. So I will assume that most of you have seen some already, but just in case, I will do a demo of what it looks like to explain mathematics to a computer. Otherwise, the whole talk is completely abstract and impossible to understand. And then the heart of the thing is explain why we want this. And I will try to be careful to distinguish what already exists today and what is science fiction. And so don't hesitate to ask if I'm saying something and it's not clear whether it's a dream or it's something that already exists. And as many people here, I'm using Lean, which is mostly the work of Leo Demura, but there are other proof assistants. So in case you didn't know, Coq was renamed Rock recently, so that one is the one you know, but it changed, switched to a new name. Isabel, Hold Lights, Mizar, and others. And the purpose of this talk is not to compare those proof assistants. I will show what I know, and I mean, we can discuss this topic if you want, but that's not the main topic of my talk. So, okay, let's see what it looks like. So, Lean itself has no visible incarnation. It's just a program that runs in the background. You interact with Lean through either a text editor if you're a human being, or some more sophisticated device if you're a large language model or something like this. But so I've got a text editor open. So this one is VI, of course. It's a nice, the nicest text editor. And I've got two definitions. Maybe I want to move the that thing a little bit here. No, not that. Because I want to see everything. So I've got a definition here. So it's a definition of a continuous function So I've got a function from real number to real number. X0 is a real number, and the definition, oh, I didn't move far enough. Anyway, you can see, for all positive epsilon, there exists a positive delta, that for all x, delta close to x0, f of x is epsilon close to f of x0, and it's ordinary mathematical notations, except for a few weirdness, like the f of x has no parentheses around x, but that's, you can still understand this, hopefully. And then there is a definition of what it means for a sequence of real number to converge to a real number L, so to a limit L. And again, you can read the definition. This is a definition you teach to first-year undergrad students. And the statement we want to prove is this thing. So you have a function from real number to real number, a sequence of real numbers u, x0 is a real number, and two assumptions. So those names are arbitrary. The H stands for hypothesis, but it's just the name I chose. So I've got a hypothesis on U saying that U tends to x0, and a hypothesis on F saying that F is continuous at x0. So it refers to those two definitions here. And the goal, what we want to prove, is that the composite sequence, F compose U, tends to F of x0. So is it clear what the statement is? And now, so this part of the screen is where I'm typing stuff, and the part of the screen on the right is where Lynn answers. So if I put my cursor inside the proof, so sorry simply means I'm sorry, computer, I don't have a proof right now. And so the computer recalls that we've used sorry, but without, what's happening here? So the right-hand side of the screen at the beginning of the proof, it's simply listing what are the objects that are fixed and the assumption. And the funny symbol that looks like a T that has fallen on the side is it means a goal. It means this is what you need to prove. You need to prove F compose U tends to F x0. And because the definition starts with for all positive epsilon, I can say intro epsilon a real number, and then and my computer is of course misbehaving just because this is a live demo. I don't know why it's doing that. Maybe let's restart the file. What is it doing? Come on, computer. Did I mess up something to the file? People who know what I'm doing. Why is it doing that? No, but why is it putting this instead? What? I mean, this icon is meant to appear at the end of the line to say that there is still something to prove. But why is it? Yeah, but this is what I would do anyway, but... Okay, you see, this is still a computer. I mean, it's misbehaving in a non-deterministic way when I'm trying to show stuff to people. Anyway, so let's introduce an epsilon. I wanted to say epsilon is a real number, but the computer is understanding this anyway. And then I introduce an assumption that epsilon is positive, and I decided to call this assumption epsilon pos, so like epsilon is positive. And now you can see the new state of the proof is that epsilon is a real number that is now fixed, and I've got this positivity assumption here, and the new goal is whatever was after the for all positive epsilon in the definition of sequence tends to, with the relevant sequence, which is F compose U. And now I need to use my assumption that F is continuous at x0, so I can, I can just specialize my assumption HF to this positive real number, and I will get new stuff, and I will get stuff that is a positive real number satisfying some assumption. And it's not important if you've never seen lean code that you remember all those commands. I'm typing mysterious things on the left-hand side, but those mysterious things, they clearly refer to the hypothesis that I have on F, and they refer to the epsilon real number and to the positivity assumption. And then I get something new, and what I get new it appears on the right-hand side, and it's again a real number. This one is called delta. It's positive, and there is this property of delta that comes from the definition of continuity of f. And then I can continue proving, I think, yeah, I messed up something with my computer, or maybe my computer is jet-lagged too, because it's doing funny things. So now I'm using my assumption on U, and I'm getting a natural number capital N, and then I can continue the proof by saying that this capital N is the one I was looking for, introduce a natural number. I am accelerating because I don't want to spend the whole hour showing this, but now I can apply, maybe I guess H delta, and I need to prove that UN minus X0 is less than delta, and I apply what is H capital N, and then I need to prove that little n is more than capital N, and this is exactly Hn. And then there is no more, and there is nothing more to prove, and I've got a small icon next to the example saying that this is fully proven, and the computer is happy. So what do you need to remember, apart from the fact that my computer was misbehaving, is that only this interaction mode, where I'm typing stuff on the left-hand side, and the computer is continuously updating the status of the proof on the right-hand side, and it's showing what are the currently fixed objects, what are the current assumptions, what is the current goal, and my comments on the left-hand side are making progress on this proof. And so, very quickly, I can show what it looks like when you apply lemmas. Maybe I can do that. Because here I had only two definitions on a statement. I was not using any lemma, any previously known result. I've chosen this example because it's just pure manipulation of quantifiers and logical connectives. So let's say if I use lemmas, so I will simply prove that the function x goes to x squared times cosine x is continuous. So as a function from real numbers to real numbers. And here, I need to apply lemmas, because I don't want to do that from first principles. And I can ask Lin, give me lemma names that could apply. And so I type the command apply question mark, and Lin is just suggesting stuff in its part of the screen. And you can see the first suggestion is a bit weird, so it's hard to read for you, but it suggests proving that if you compose the function I had with the inclusion of real numbers into extended real numbers, I get something continuous. So it suggests proving something harder, just this is one lemma that applies. And then it suggests something reasonable, which is to apply a lemma called continuous.mul, and there will be new sub-goals, continuity of x goes to x squared, and continuity of cosine. So that looks like a very sensible suggestion to pursue. And just for fun, we can have a look at what are the other suggestions, because some of them are pretty fun. So some of them are pretty non-committal, like this one suggests to prove that for every set in real numbers, if S is open, then the preimage under my function is open, which is like using the general definition of continuity in topological spaces, which is of course a very bad idea here, but indeed it would be enough to prove that. And it also suggests, so what would be a fun one? I mean, that one is really stupid. It suggests you could prove that the real numbers form a discrete topological space, but Lin really means the real number as the target of the function is discrete, and then prove that the preimage of any singleton is open. Now that would be enough, yeah, sure. And I think it also suggests that if I prove that the source is discrete or is empty, I think if I search on empty, maybe, yeah, if I, no, that one does not really return. Sometimes, depending when I upgrade Lin, the suggestions change slightly. So the other day I gave this talk and it suggested if you can prove that real numbers, the set of real numbers is empty, then you're done, because any function from the empty set is continuous. So, let's accept the suggestion that made sense. And then I've got two goals, and this is also an opportunity to see what happens when the proof splits into two tracks. So continuity of the squaring function and continuity of cosine. And this I can, again, type apply question mark. And this time there is only one suggestion, and the reason why there is only one suggestion is because this lemma is directly in the mathematical library. And same for the continuity of cosine, I can just call this exact continuous cosine, but I don't have to know all those names because I can just write this apply question mark and Lynn will say things. And of course, in this case, even this is too much work, and you hope that the computer can prove this. And indeed, there are more sophisticated commands that you can give. And for instance, here you could say fun prop, and this will just prove the whole thing in one command. And this, what this fun prop word is telling Lynn is it's telling Lynn to repeatedly apply the properties of functions that are known in its database of already known lemma. So the purpose of this file is to show you that you don't have to go back to the axioms of mathematics and the definitions like I did in the previous file all the time. We build on top of previously existing results, and we can apply lemmas that have already been proven, and this is of course needed if you want to do anything sophisticated. And just very quickly, let's see what it looks like to do a bit of algebra. So here I've got a definition. So of course, Lynn already, the mathematical library of Lynn already knows what is a group, but I'm telling again what it means to be a group. And the definition I've chosen, there are a couple of options. I say a group structure on G extends the fact that G is endowed with a multiplication and an inversion function and an element denoted by 1 by the following 4 axioms. One axiom says the multiplication is associative, and then there are 3 axioms involving 1 and the inversion function. So because I said here in this extend clause that G has an inversion function, I get access to this notation A inverse, and I've got this axiom saying that for all A in G, A inverse times A is 1, where 1 comes from the assumption that I had here that G is endowed with an element denoted by 1. Okay, and if you teach group theory, maybe you have a 4th axiom saying that 1 is also a neutral element from the other side. So for all A times 1 is A. So let's prove, just to see one proof involving algebraic structures, that it follows from the other axioms. So I've got now a lemma saying that using this definition, if I've got a group G, and then for all A times 1 is A, and I've got a small calculation, and the important thing is that you can read this syntax, what the calculation is doing, and here's the justification for each computation step. They invoke the axioms that I've put in my definition. Okay, so just doing the very beginning of abstract algebra looks like this. Are there any questions about what it looks like to explain mathematics to Lynn? No? So let's move on. So why would we do that? So here I've listed 5 reasons to do that, and I will go over those 5 reasons for the rest of the talk, but I can already read them. So this is good for checking, explaining, teaching, creating, and having fun. So, of course, the actual reason we do that is the last one, but I'm kind of contractually obligated to also discuss the other ones. So, checking is the most obvious reason. So I'm still listing as the first reason because it's the first one that comes to mind, but to me it's not the most important reason. So let's still discuss this reason. With that, such programs, you can reach indeed superhuman certainty that some proof is correct. I mean, it's much more reliable than humans at checking proof. And as a mathematician, you get to check your colleagues' work, and if you're, I mean, not maybe for the youngest in the audience, but when you get a bit older, you have to write something that is called a referee report. So people submit proofs to specialized journals, and then other mathematicians need to check the proofs, and it can be very painful if you do it properly. And so the dream, from the referee's point of view, the people writing those referee reports on new contributions, is just to check relevance. When someone says, here is my new theorem, and the first task of the referee is to say, do we care? Because it's very easy to produce new theorems with correct proofs about objects that nobody cares about, or just proving properties that are not relevant to anything else. And so this is part of the job, so let's do that, and let's not leave that to computer. And let's also check that there are new ideas in the paper, especially if the paper is submitted to a very prestigious journal. You want to make sure there are new ideas that could be reused to do other things. And so let's do that. Let's not leave that to computer, but the proof checking, let's leave that to computers. So that would be the dream. And now, it's getting even worse. No, even the clicker is not working. So there is no short-term hope to do that because just checking mathematics on computers is too time-consuming. Especially if the computer misbehaves, but even under normal circumstances, you just spend a lot of time explaining proofs to computers. So at least in the current state of technology, we need to focus on only some of the proofs. So maybe there could be proofs that are too big to fit in a human brain, and we are afraid that people lost track of something because the proof is too big. Or sometimes the proof is not, it's not that the proof is too big, it's that there is a very technical fragment that is maybe only a couple of pages long, but that very technical fragment we want to check. So for instance, this is what happened in 2020. So Peter Scholze from Bonn wrote messages to the community of people using proof assistants, especially Lean, saying, yeah, I've got this theorem that he proved with Dustin Clausen, and so this is what Scholze wrote on a blog post. He thought this theorem was super important, and it doesn't matter what the theorem is about. It's part of his dream of unifying arithmetic and analysis and geometry in condensed mathematics. So he was convinced the theorem was extremely important. He had a lot of trouble proving that theorem, and he was, so something very important, he was convinced that this theorem would never be checked, it would be used as a black box, and the mistake could go unnoticed forever. And because what happens with Peter Scholze is, so he's extremely popular, and whenever he says, whenever he puts something on internet, all over the world, there are groups of people reading what he writes. So this happened with condensed mathematics, and he was very happy to see that everybody was, as usual, working very hard to understand what he was doing, except that everybody was keeping the same proof. And this proof he was worried about, and he had not a good understanding of why the proof was working. And so he asked us, could you check, just those, I think it was something like 10 pages he was really worried about, and the rest was fine. But of course, those 10 pages, if you expand them to actually understandable mathematical text, is more than 10 pages, but still you should think it's a small but very technical fragment of mathematics. And so a team led by Johan Comlin started working on this, and in 6 months, the technical point was checked, and then there was still work to have a nicer statement, but the part that Scholze was worried about was checked within 6 months. So in this room, I think we are quite a few people who contributed to that, because Ricardo contributed, Bhavik contributed, and Filippo also. Filippo is also here, yeah, and from people who are here today, there's those names. Ricardo Brasca is in the back of the room. You've seen Bhavik 1 hour ago, and Filippo is also somewhere in the back. So it was a teamwork checking that. And we checked other results recently. So with Oliver Nash and Floris von Dorn, I did this sphere reversion theorem by Smale. So actually we formalized something much more general, some more abstract result by Gromov about some version of the H principle by Gromov. And the reason why we chose this problem is that many people were convinced proof assistants were good enough only for algebra and combinatorics or logic, but things that were really geometrical with actual mathematical content and not just pushing symbols around would be inaccessible. And of course, I claim that there is no such distinction, and so it was actually completely possible to formalize that style of mathematics. So we did that, and then there was recently some additive combinatorics done by Terry Tao and a team on this on Martin's polynomial Feynman-Ruscha conjecture, and Bhavik worked on those Ramsey numbers, formalizing these Ramsey number bounds, and this is graph theory. So again, rather combinatorial things. I mean, the first one, I mean, additive combinatorics, I mean, it still involves some probability, entropy stuff, so you should not think it's not combinatorics as in just playing with finite numbers. It's, additive combinatorics does interact with mathematics at large. And currently there are many ongoing projects in all kinds of mathematical branches. So Carlson's theorem on almost everywhere convergence of Fourier series for LP functions is really hard analysis. So it is basically Carlson's Abel prize, and so very hard harmonical analysis. Fermat's last theorem has a bit of all kind of mathematics, and also very algebraic category theory stuff around infinity cosmos, led by Emily Riel. So those are the most active projects nowadays. Okay, so now let's move to the next motivation, which for me is the main one. I mean, this one and the next one are the main motivation. So the motivation is to explain mathematics. So the main point is that in traditional math writing, the author decides the level of details. You cannot write every details unless you're just doing the very beginning of an undergrad lecture. So you need to leave out some details, and the author gets to decide. And as the reader, if this is not enough details, or maybe you're jet lagged, or maybe this is not your area of mathematics, then you're just stuck. So the goal is to use formalized mathematics to let the reader decide the level of details. So, and it does not mean always decide I want more details. No, because if you ask for every details, it becomes unreadable, but you need to be able to decide. So what we want is some kind of mathematical document where you can continuously zoom from heuristic high-level overviews to full details and back dynamically. So I will show a prototype of something I'm doing with Kyle Miller. So maybe I will first show, so this is a lean file, and just I show you so that you can see the scale of this lean file. So we've got a lean file of, I don't know, about maybe 30 lines of code showing something about topological spaces. It's not important what we are showing, but there are something about topological spaces and continuous functions. And this is a lean proof that has been typed by hand by me, and just in the way I showed at the beginning. And then our program, which is itself a program written in Lean, which is also a programming language, turns it into this web page. And this web page, in the beginning, it looks like just ordinary mathematical text. So this is generated automatically and in a deterministic way, not using LLMs or anything like this, to do sentence. So somewhere I say that when in the Lean code, you see topological space in one word like we had before. Somewhere I've written once, when you see topological space X in English, it should become a topological space, but then the sentences are done automatically. And so you've got the statement, and you can read it without any training in formal methods. You need a training in general topology, of course, but no computer stuff. And then there is a proof, and this proof, the proof you see here is about the same length as what you would see in a textbook. So we took the proof from a nice textbook in topology written by Nicolas Bourbaki, and this is the proof that you would find in the textbook. And if you don't understand something, you need to go to Bourbaki and ask questions. But here, there are two things you can do that you cannot do with the book. First, you can click on those small ovals here, and get the proof state at this stage. So here I clicked on one of them, and on the right, I've got a current proof state with English sentences, and what are the objects, what are the assumptions, and what is the goal. And if I move further in the proof, I have more things, and this is already quite some progress, because you know exactly at each point in the proof what are you trying to do now and what have been achieved already. And more importantly, there are small plus signs. So you can see the second sentence says, one can see it suffices to prove something, and if you don't see it and you're reading a book, then you're stuck. But here there is this little plus sign. I can click on the plus sign, and if I click, I get a new paragraph of text saying, we see this by the following argument, and here I've got a paragraph of text. And this paragraph of text is still not fully detailed. There is this sentence, for instance, one can obtain. Why is it true that one can obtain that? You click on this, and it says, using our assumption that y is regular and assumption that v prime is a neighborhood, proves one can obtain. And if maybe you don't know what is a regular topological space, so it's not enough for you, you continue clicking, and you see there is a lemma that is invoked, and you can put your mouse cursor on top of this lemma name to get the statement of the lemma, and so on. Okay, so is it clear what this does?
What happens if you click on the first plus before let x be an element of x?
To prove f is continuous, by definition, we need to show, because you see the conclusion was not manifestly for all x something.
Yeah,
so. So here it's the first proof was actually unfolding. I switched to another clicker. That's funny. The proof was f is continuous, and so it's not clear that it starts with for all x, and so the proof started with let x, and so yeah, this is just explaining this. And depending on how you define continuity, it's not clear that it starts with for all x. So here, the definition of continuity that we are using is a function is continuous if it's continuous at every point. Okay?
What about the lemma? So can you find the proof of the lemma?
So right now, you cannot. So in this prototype, it's only a single file with no cross-referencing. But the idea is that, of course, in the final software, you will be able to click on the lemma and see the proof. Okay, so let's move on. So I really hope this will change how we write and how we read mathematics. And again, the input is the lean file. And the lean file itself is not huge. I mean, maybe I should click on this expand all button to see what happens. If I click expand all, and then it will click all the plus sign, and the proof will get pretty long. And it gets pretty long, and without going back to the axioms, it's still referring to lemmas, but it's still much longer than what was typed in the lean file. So in the lean file, you type whatever you want, use automation, search for lemmas and stuff, but then after doing all that, instead of having a lean file that only you can read, or only lean experts can read, you have this web page that anyone can interact with. And yeah. Okay, how am I doing on time? I don't even know at what time I started, because we started late.
We started around
4:30. Okay, so I'm halfway through. Okay. So then the next motivation, that will be the topic of a full talk tomorrow, so I won't spend too much time on this, but still for people who won't be able to come tomorrow, or maybe for advertisement for tomorrow's talk, I'll mention teaching using lean. So here when I say teaching, it's not the same thing as the previous point. The previous point, explaining mathematics, was just explaining mathematics to people who already know what is a mathematical proof, and that could be explaining mathematics to your colleagues, researchers in mathematics. Here I'm really talking about teaching how to prove things and write proofs to very young university students. So I've been using lean with first-year undergrad for quite some time now, for 6 years in Orsay, in France. And what we are doing is we are reproving stuff that they have proven in the first semester at university about sequences of real numbers and continuous functions from real numbers to real numbers. But they reprove those things in Lean with the goal of being able to write proofs on paper. So Lean is not the end goal. Lean is only a tool that I'm using as an intermediate tool to explain what it means to prove something rigorously in mathematics. And then the goal is really the pen and paper proofs and also reading pen and paper proofs for students. And in the beginning, for the first 2 years, I was just using the normal proof language of Lean that you've seen today. But I was a bit disappointed by the skill transfer to paper. So students were able to prove things in Lean, but then when I gave them paper and pens, they were no longer able to prove things. And so because of this, I started working on a custom input language that I will show briefly. And this input language is harder to write, but easier to transfer to paper. So this is one example taken from the exercises that my students do. I mean, they work on the French version, but this is the English language version. So you see the statement is a bit different. It's more explicit. What are the objects, what are the assumptions, and what is the conclusion. And there is a bit more words in the assumptions too. Instead of saying sequence tends to UL, I write U tends to L. And then the proof, instead of intro epsilon, I write fix a positive number epsilon. Since U tends to L and epsilon is positive, we get N1 such that, and then you get the property of N1. And I want to prove that maximum of N1 and N2 works. I fix N bigger than max N1, N2. And you see, so there are two things going on here. First, there are those sentences. So this is the controlled natural language aspect of it. So it sounds like just natural language, maybe a bit repetitive, but it's just as rigid as before. So if I delete one character, then I get an unexpected identifier error, and it's just still rigid computer code. But it reads like sentences, and it gives students good habits, just pre-made sentences they can reuse on paper. And it also makes it easier for them to keep track of the structure of the proof. You see, the issue with the info view, the right-hand side of the screen, shows you a very localized view of the proof, what you're doing right now, but the left-hand side is basically unreadable and doesn't really give you the proof. And I don't want to spend too much time on this. You will get details tomorrow, but note that there is also some automation going on. Like I fix N bigger than max N1, N2, and then on the next line, I just claim that N is bigger than N1, and there is no justification whatsoever. I just say, since N is bigger than N1, we get something. So the computer also figured out a proof of this N bigger than N1 from the fact that we assume N is bigger than the maximum. So of course it's a stupid proof, so it's definitely something we don't want to see any explanation about this step on paper. So what I'm saying is that when I'm using Lean for teaching, I also don't want to see any explanation here. And if you use just the ordinary Lean language, you would need to put some justification here. And in the same way, I say it suffices to prove, I mean, the goal at that stage is to prove that the absolute value of Vn minus L is less than epsilon, and I say it suffices to prove those two inequalities, and so there is no justification here for these two. So this is what I'm doing for teaching. So we've done 3 of the motivations. Remember, I gave a list of 5 motivations for formalizing mathematics. So that one is number 4, creating new mathematics. So let's say we're doing mathematical research, and we want to know whether this kind of tool can help us. So with the current state of technology, I already told you it's very time-consuming to explain mathematics, so it wouldn't be honest to tell you that whatever your mathematical research is, you would win something by doing formalization as you go. I mean, by doing formalization as you go, you will probably get slowed down to just not moving at all, except if you're in an area of mathematics that is particularly suitable. But still, this gets easier every day. So at some point, we hope that it will be doable for everybody to just formalize things as part of their research. So what is already existing is that it's very easy to tweak definitions and statements when they are formalized. When you write a long mathematical paper, it's really awful when you realize on page 50 that you need to change the definition of page 1 because it's almost the definition you wanted, but not quite. Because when you're doing mathematical research, and the definition is not always fixed from the beginning, sometimes you've got to make up new definitions. And so when you're in this situation, you're very worried, because maybe if you change a statement of the lemma on page 3, and you're not quite sure when it was used, because maybe it was used implicitly sometimes, and you don't dare changing anything, or maybe you've permuted 2 paragraphs for exposition, but you're not quite sure whether it became inconsistent in terms of exposition. And with a proof assistant, there is nothing like this. You just tweak the definition, and the proof assistant rechecks everything and tells you this is no longer true, or at least this proof breaks, and this proof is still fine, this proof breaks, and you can just go fix everything and be confident that it works and you've not broken anything. This also applies especially in situations where you've got explicit constants. Say you're doing estimations in analysis or in combinatorics, and you've got explicit bounds, and somehow at some point you lose faith in your previous explicit computation, you just start adding bigger constants just for security, for safety. And when you have a proof assistant, you can just make sure that everything goes through, so you keep motivated to have tight bounds, and you can go on. You can find unnecessary assumptions. It's very nice at the end of a proof when Linz tells you, you never used this assumption, and you realize, hey, that's true, I never used this assumption. And just remove it, and you know that it's all good. So searching for mathematics should become much easier. It's already a little bit true, but it's not completely true. Here the dream is when you search for something, you want to know if some result is already known, or maybe some variation of some statement is already known. If you just Google the statement, it's hard to get an answer. And if you ask a large language model, and the large language model is so happy to please you that it will just simply make up some result, and you also don't know. So the hope is that if everything is formalized, then you can search through this formalized literature, and you're sure, because even when you find something, when you find a result, maybe you're not quite sure if the notations are the notations you're used to, or maybe there are variations in the definitions. Even if Google does turn up a paper, but you need to make sure that when the paper says this data is, I don't know, admissible, then it really means what you think it means and not some variation. And so here everything should become much easier. And of course AI may help, so we had a whole talk by Bhavik about this. Maybe it will be feeding easy proofs or suggesting analogies, and I will have one more slide about that, but this is not yet useful, but it could become useful. And something I will insist on is the way formalization encourages clean abstractions. So those proof assistants, they really like abstractions. And it's much easier to prove something abstract than to do concrete computations and examples in those proofs. So we saw this morning several talks by students here, and the most difficult thing was proving what was it? Differentiating functions from real numbers to real numbers. This harmonic oscillator talk that we had was clearly the most painful. It was too concrete, not abstract enough for the proof assistant. So one slide about AI. So LLMs are currently useful to search for existing lemmas and definitions. So you can, there are various websites where you can type natural language queries, and some LLM will search for existing formalized statements that may be related to your query. So it's already somewhat useful. So of course it's not reliable, but that's it could turn up useful things. And Bhavik already explained how LLMs plus Lean got a silver medal for some value of getting a silver medal at IMO last year. But today the proof capabilities are not yet useful on a daily basis for people using proof assistance, partly because as you've seen, all those companies like DeepMind or OpenAI, they do not release any tool that you can use in Lean. So they are all, everything is secret. And so maybe if someday we get access to those tools, they may be useful, but they are currently not. So I want to now insist on this story of clean abstractions and how it can help you be better even on paper as a mathematician, because you kind of think a bit differently. And again, it comes in addition to what you already have. So you don't have to forget any of your previous mathematical knowledge. You get some extras coming from the habit of formalizing mathematics. And let's see a couple of examples of what those extras could look like. So first, there is a whole families of extras that have to do with thinking in terms of induction principles. So when we say mathematical induction to mathematician, they always think about the same statement. So you've got P, a property on natural numbers. If P 0 is true and for all n, Pn implies Pn plus 1, then for all n, Pn. So this is induction on natural numbers, and this is what we call induction on in mathematics courses and among mathematicians. But when you start to do formalized mathematics, you start to see induction principles everywhere. So what does it mean, induction principle? In a vague sense, it has this shape. There is a property on some kind of mathematical object, and there is some kind of propagation step and some kind of initialization step, and the conclusion is your property holds for all your objects. Okay, so it's this general shape. So I don't remember which example I put because I'm just cycling through several examples in my talks. So that one is induction on connected Lie groups. So say you've got a property on a connected Lie group, and if this property holds near the neutral element of your group, so that's the initialization, and for every GG prime, if you've got PG and PG prime, that you've got P of GG prime, so your property is stable under multiplication, then your property holds for every element of your connected Lie group. So if you don't know what is a connected Lie group, you just skip this example, but you just notice that it looks very much like induction for natural numbers, but except that it happens on some fancy mathematical object that is a connected Lie group. And I put this example because in the first semester I was teaching Lie groups and then Riemannian geometry as a graduate course in Orsay, and I realized that I was just repeating the proof of this induction principle over and over again. And I thought that clearly in a proof assistant, I would just state the induction principle. I kept saying, yeah, remember in a Lie group, connected Lie group, every neighborhood of identity generates a group, and you can, an inversion is continuous. So if you've got a neighborhood of identity, intersect this neighborhood with the image under the inversion map, you get a new neighborhood of identity. And I was just saying this over and over again, and now I gain this little superpower that I just say, by induction on my connected Lie group, I only need to prove those two properties. So let's do a bit of analysis now. Let's do some induction principle for functions between finite dimensional real vector spaces, and if you know about manifolds, you can put a vector bundle over a manifold if you want. So I've got two finite dimensional real vector spaces and a property of pairs, an element of E and an element in F, and probably it's better to first read the conclusion. We want a function, a smooth function from E to F, so that for every x in the source, P of x, F of x. Okay, so maybe that would be some examples would be, for every x, my function f is smaller than epsilon in norm and non-zero or whatever. I mean, some function, some property of f of x, and maybe depending on x itself. So, yeah, maybe the simplest example would be, assume I've got a continuous positive function on E, then there is a smooth positive function that is smaller than f, f0. So f0 is a continuous everywhere positive functions, and I want a smooth everywhere positive function smaller than f. And how do you prove that? I mean, you need to do some kind of induction, and it's some kind of initialization, and the initialization is that for every x in E, there is a solution on a neighborhood of x. So there is a neighborhood of x, and a smooth function on this neighborhood, which works in this neighborhood U. And the kind of the propagation condition is that for every x in E, the set of y so that pxy is true is a convex set. And then there is a global solution. How do you prove this induction principle? A quiz for the audience. So I've got my local solutions, and I need to glue them to a global condition using some kind of convexity. So in the example I gave before, the thing that would be convex would be simply positive numbers less than my value of my continuous function at that point. So this convexity condition is trivially satisfied in my example. Why is the local existence satisfied in my example? I've got my continuous positive function. Near every point, I can look at a compact neighborhood of that point, and on this compact neighborhood, there is a constant function that is smaller, that is positive and smaller than my continuous positive function, simply because my continuous positive function reaches its lower bound on a compact set. And the proof of this induction principle is partition of unity. So you glue local solutions by partition of unity. And so if you know about partitions of unity in differential topology, we are just redoing the same proof over and over again, building local solutions and then explaining, no, I take a partition of unity and I take this sum of rho I fi, and this is a locally finite sum, and then the convexity stuff and so on. But here, I just have an abstract statement where there is no partition of unity anywhere in the statement. It's all encapsulated in what you can do with partitions of unity in this statement. And now, so that was about induction principles. And now, let's see how the example that we did at the beginning, where was it? The basic stuff that we had. So continuity implied sequential continuity. This is the proof that I did for you, but it's not at all the proof that you would see in the mathematical library of Lean. The proof that you would see in the mathematical library of Lean would be like this one, and this would be the proof. So there is this definition tends to instead of my sequences tends to, but I mean, okay, there is the spelling is slightly different, but trust me, it's exactly the same statement. And the proof is 3 lines of algebraic manipulations and inequality. So what's going on here? And there is no quantifier anywhere. No for all, no exist at any stage in the proof. And what happens if you go to the LaTeX version of this proof? This is the LaTeX version of the proof I've just shown. So assume this and that, and then do this little computation, and that's the proof. So what's going on here? It says direct image under X of neighborhood of x0 is less than neighborhood of fx0. And what is this neighborhood? It's kind of the set of points that are very close to x0. And I will explain that later. So it says direct image under f of the set of points that are very close to x0 is contained in the set of points that are very close to f of x0. And direct image under U of the set of very large natural number is contained in the set of points in real numbers that are close to x0. And then the proof under these two assumptions of the fact that f compose U sends very large natural number inside points that are close to x0 is just this 3 lines computation. So what's going on here is that when you do limits, there are tons of variations on limits. So you could have limits of a function at a point, or maybe say f is a function from real number to real number, limits from the right, and maybe f of x could go to y0 from the left when x goes to x0 from the right, or maybe f of x goes to plus infinity when x goes to x0, and there are limits when x goes to x0, but without being equal to x0, so pointed limits. And so how many definitions are we talking about? So even if you stick to functions from real numbers to real numbers, the target could be any of those possibilities, and maybe also x could be constrained to be in some subset, maybe rational values of x. And so let's say there are 16 variations for the source and target, so we are talking about 256 definitions. And now, what we had before, the proof we had before was actually composing two limits. So we need a lemma that says limits compose. How many lemmas are we talking about? So for instance, one of them would be if f of x goes to y0 when x goes to x0, and g of y goes to z0 when y goes to y0, then the composition goes to z0. So how many lemmas? People who are good at combinatorics. So now we've got the source thing, the intermediate thing, and the target thing. We've got 16 possibilities for each. So we are talking about 4,000 lemmas. Okay, so how do we prove those 4,000 lemmas when we teach first year undergrad about limits of functions from real number to real number? And we've got a very powerful trick. We do 2 cases, and then we say all the other cases are analogous. But now I'm running low on time, so I need to prove those 4,000 lemmas very quickly, and this is why the technology that was mentioned in the previous slide come in. So that you can learn some mathematics also from this talk. So given any set x, you can embed the power set of x, so P of x is the power set of x, so every subset of x goes into a mysterious f of x, which are generalized subset of x. And for instance, among those generalized subsets of real numbers, there is a generalized set of very large real numbers, or the generalized sets of points that are close to x0. And there is a definition, but hopefully it's written small enough that you cannot read what is the definition of how this is implemented. So those generalized sets, they are called filters. And we can define very rigorously what it means, what we call the generalized set of very large natural numbers. It's implemented as a collection of subsets of R. And the generalized sets of points that are close to x0, it's implemented to simply the collections of neighborhoods of x0. And there are axioms that those collections of sets must satisfy to be called generalized subset of x. And then you can extend the order relation, so inclusion of sets in x extend to some order relation on filters. And I've got this inclusions of ordinary sets into generalized set, which is order preserving. And then I can extend a direct image and under an inverse image. So all those things extend to generalized set, and in the sense that, yeah, if you've got an ordinary set in the power set of x, you can take its direct image under f, get an ordinary set in y. But if it's a generalized set, you can still also do it. And this compose the way you think they should compose by notation. So when the star is down, this is covariant, and when the star is up, this is contravariant, just like direct image and inverse image. And you still have the adjunction between direct image and inverse image. And now you can define limits by saying that a function phi from x to y converges with respect to a generalized set g on y along a generalized set f if simply direct image of f under phi is less than g, where less than is again this order relation that extends the subset order relation that we had on ordinary sets. And now I'm really low on time, so let's do 4,000 proof very quickly, and that's done. That's now the composition of limits. I assume phi sends this generalized set F into G, and psi sends G into H, then using that direct image is functorial, so distributes over composition, and also that it's order preserving, so it's monotone. I had my phi F less than G. When I apply psi star, it's still less. And then by assumption on psi, this is less than H, and that's the end of the proof. So what was this? That was 100% mathematics. No computer science, no computers involved. And it doesn't exist in the real world, in the sense that the theory of filters was invented in some form in the 40s, but not developed enough. I mean, most people nowadays, they don't learn that. It's very rare that people know about filters, and when they know about filters, they don't know about this way of looking at filters. And if you look at proof assistance, it's not only mathlib, the math library of Lean, it's everywhere. In every proof assistance, filters are everywhere, and they handle all limits and also other things. And once you start thinking like this, there is no going back. And you can never think about limits in a different way. So it's a really, really nice story that I had no idea this existed before I started using Lean. So it was really, and I was doing differential topology and calculus and stuff like this. And so the last thing I wanted to say is that the actual motivation for doing all this, it's a lot of fun. And it's a lot of fun as a group. So it's very collaborative. And this is, for instance, what Terry Tao really likes about this. He's very into large collaborations. And he gave a very nice talk at the Joint Mathematics meeting, so the annual AMS big meeting last year. And he wrote several blog posts about this. And I want to, do I have 3 more minutes? Or, yeah. So one thing that he likes and other people like for this collaborative thing is a tool that I built indeed for the sphere eversion project, which is this blueprint technology, and especially inside the blueprint technology, what is really useful is those graphs. So what is this kind of graph? So maybe if we see a live one, it's easier to understand. So this is the dependency graph of the Carlson theorem. So Carlson, remember, this is the story of Fourier series of LP functions converging almost everywhere. So super hard harmonic analysis theorem. And if you look at this graph, if you zoom in, you will see that every node is a statement of some lemma. So if I click on this node, I can see the statement just in ordinary mathematical. So that was typed using tech. And so there is a statement. And this statement, you can see in the graph, it's a green statement. So that one is fully formalized. You can jump to the Lean code by following this link here. I won't do that. So this is already done. But you see, it's green, but it's not dark green. The reason it's not dark green is because it depends on stuff that is not fully green. So here you can see this, the boundary of this ellipse is green, but it's not filled in green. So it means the statement has been formalized. So this is all explained if you click on this legend button. So the statement has been formalized, but not the proof. So this forest complement, whatever it means, it depends on this thing that was not yet formalized. And you also have things that are blue, which means that they are ready to be worked on, because all the prerequisites have been done, and this is an available next target. And you can, so this is only the statement, but if you click on the LaTeX link, you will go to the ordinary pen and paper proof. You can just see the statement and the proof, and so this is all made so that it's easy to participate in such projects. So if you're interested in harmonic analysis, you can decide today that to go to this website, which is public, and find something that is blue but not yet green, and decide you will work on this lemma, and you know it's a good target. You can discuss it with the coordinator of the project, which is Floris von Dorn in Bonn. And if you manage to prove this lemma, also once you've convinced Lean that you have a proof of this lemma, Floris, who is managing the project, does not need to trust your mathematical ability. because he will simply trust that Lean check the proof, and you can contribute to this exciting project without needing to first earn the trust of Floris van Doorn or his collaborators. And so who's doing it? So I said already that Leo Demura is the man who created Lean, originally at Microsoft Research, now at Amazon Web Services. And Lean is an open source project, and the library is also open source. They are open source in slightly different ways, to be honest. So the Lean itself is a super technical software. It's really crazily complicated. And so the source code of Lean is on GitHub. You can find it. You can say, I want to contribute to it. And if you propose a change to the core of Lean, I can tell you what will happen. Leo Demura, and if you've never done anything in this direction before, Leo Demura won't even look at your code. He will just close it, saying, this is critical code. If you break something here, everything will break. And so I don't want contribution from people who know nothing about how Lean works. Whereas for MathLib, so the number of actual contributors to Lean is like, I don't know, core contributors are maybe like 5 people really actively working on Lean. Whereas the mathematical library, not only is open source, but there are like 500 contributors, and we are at about not far away from 2 million lines of code, I think 1.8 million lines of code, and there is work for a lot of people. So of course your first contribution would need a lot of work to be in good shape for inclusion in MathLib, but it's much more accessible than working on Lean itself. And so yeah, currently there are still very few mathematicians using proof assistants. If you just take a random mathematician on this planet, they will know nothing about any proof assistants, but almost all of, but first this number is growing pretty fast, and people who do use some proof assistant, they basically all use Lean. So there is a very active and welcoming forum if you want to start playing this game, and all the links can be found from this leanprovercommunity.github.io. So don't hesitate to join the fun. I stop here. What? So sorry, I didn't get that.
So the translation from Lean code to like natural language text, one of the first ones that you showed. So like, what were the kind of deterministic code? I mean, was it like regular expression based? Like when you said X is of the type of topological space, to let X be a topological space, right? So how did you really translate that? I mean, so what was the deterministic code like?
So there is that's a pretty complicated pipeline. I mean, I could easily give just a 1 hour long talk on how this thing works. So it's kind of hard to give a short answer to this question, but it may be good to realize that it's not only doing, so maybe I collapse all those things because it's frightening. So first saying just let X be a topological space, this is a very straightforward translation, because in the beginning what we had is in the Lean code, do I have my Lean code? In the Lean code, there is an auto implicit here, but there could be just a declaration that X is a type, and then one type class topological space on X. But it's already merging two things. It's already merging the sentence let X be a type in any universe with let's endo X with a topological space. But then for Y, it's already doing a bit more work, because Y is a type, it has a topological space structure, but then a bit further away, there is this assumption that Y is regular, and then in the sentence it becomes let Y be a regular topological space. So there is an algorithm that is just running through the statement and collecting informations about the various types that appear and trying to merge them into a piece of sentence. So that's one thing. So turning the statement into a set of sentences, and again, this is a completely deterministic thing. So there is no, because you can also do that with LLMs, but then there is, then you don't know whether it's correct or not, because it could be completely wrong, and so here it's completely deterministic. And then there is the proof. So what happens in the proof is there is a component which simply takes a proof term and makes a sentence out of it. So if the whole proof is a proof term, only this thing will run, and it will handle nesting. So if your proof term is nested, it will create some pluses sign for just expanding on the different proof arguments that goes into as subterms of your proof term. So that's one other component. And then every tactic has its own handler, so the own little program that takes the tactic invocation, the tactic state before the proof, after the proof, what goes into the argument, and builds sentences or paragraphs out of it. So it's quite a lot of metaprogramming code. So what's wonderful with Lean 4 is that it gives you access to all its internal state, and you've got a lot of work. And it's not at all, maybe I should have clarified this. When I said that the input is this text, it's not only this text, it's this text seen by Lean. So it's not like we are not giving just a string of characters and to the program. It uses the front end of Lean to parse all this and access all the intermediate states that Lean sees in this proof and build everything from there. That's why it's crucial that this program that generates the web page is written in Lean itself and has access to all the internal state of Lean while building the web page. Did I answer the question a bit? Or?
Yeah.
We can talk more.
So I'm curious about the status of the other direction, like from natural language. Can one generate Lean code, which is of course now done by humans, but I mean, is a way to automate it, or the efforts to automate it?
Yeah, okay, so just for clarification, there are two very different things, because I've shown some version of this in my teaching library, but that was, I guess, not what you're asking for, but just for clarity, whereas my teaching stuff. So this is a case where it looks like natural language, but it's extremely constrained natural language, and so this library could not take just a free-form text and do anything with it. So this is completely deterministic, and it has no... this is a rather easy task. I mean, it's a lot of work to tweak the automation level and stuff like that, but the language part is completely straightforward, just parsing prepared sentences and so on. And then there is something completely separate from this, which is just give to a computer just a page from a textbook, or maybe the text source, or even a PDF file. Nowadays, LLMs can take just the PDF and output the text source very reliably, so the difference no longer matters. And then turn that into a Lean proof. This is, of course, a very active area of research, and Bhavik already mentioned that it's part of the pipeline for alpha proof to be able to do that. And it's, of course, it's an important topic because, again, mathematical formalization is time-consuming currently, and so at least if we could get started automatically, so maybe not a full auto-formalization, people call this auto-formalization, but maybe already if the computer has a kind of a plausible-looking translation for the statement and for the main intermediate claims, that would be useful. Because if you know ordinary research-level mathematics proof, they do not look like a sequence of applications of inference rules and logic rules. They look like a sequence of statements. You state this, or maybe you state this, and it follows from that, but it's really a succession of statements, and already having a program that takes an ordinary math paper and turns it into a succession of statements that are formalized would already be very useful. And there are many groups working on this, some of them working in the open, and some of them working in private companies that do not share anything. But so, I mean, somehow, something should happen. I mean, currently there is nothing you can really use as an end user. Siddhartha is working here on this topic with colleagues, and so there will be something usable in the near future. I think this is a much more realistic prediction than just, I don't know, general artificial intelligence or so. Yeah, nothing really usable yet, but it's coming, I guess.
Any other questions?
Okay, let's thank Patrick Massot.